going to have these two formulas. For chapter 9, I said it's still about hypothesis testing. What's the difference? Well, the big difference is now we have two proportions that we're trying to estimate. Like what? Well, maybe we want to make a comparison. Okay? So for example, you're going to have a P1 and you're going to have a P2. Better use a different color. There we go. These are from two different populations. That's one of the big differences. It's going to be two different populations in chapter 9. It was so close. And then here, these are going to be two different what? Two different. If I put the hat up, what's that going to mean? Yeah, these are samples, right? And they're sample proportions, right? By the way, okay, everything else is basically the same. And you will see that. You will see that chapter 9, the way I describe chapter 9, it's what we did in chapter 8, it's what we did in chapter 7, but the formulas get very ugly. That's the only difference. There's not really much new in chapter 9. It's just, if you want to make comparisons between two different populations, the formulas get ugly. And I'm going to show you that here. Here, take a look at the formula sheet once again, right? Chapter 8, these are the formulas. And we're only doing the first two on our quiz, right? Let me show you chapter 9 formulas. They're right below. Ha 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 ha! And you must memorize those. No, I'm kidding.
No way.
No way. We're not even memorizing anything in this class.
I'm not going to believe.
So, the equation's really that much different? Or is it
They're really not much different. They're really not. It's because I'm using two. And I will go through these formulas with you, right?
Now, could you, before you were to solve that equation, could you just do the combinations of the two sides on the top and bottom?
Whoa. I can't sum it up that quickly.
All right.
I can't. I wish I could. I'm just not that sharp, I guess. No, I will show you how to use these. And what's truly amazing about doing this homework is that you start to realize that, oh, this actually helps me understand chapter 8 a little better, and it helps me understand chapter 7 a little better. Because if I can do it with these formulas, you go back to those other ones, it's no problem at all. It's, yeah, it's not much different. We will see. So there's a method to the madness here, ladies and gentlemen. We're going to try this. Now, I'll go back to the slides. Again, I'm going to be flashing things at you that you don't write down. And then I will also switch over the notes when I think, hey, we better write it down, right? To me, this is the main idea, that there are two different populations, there are two different samples, and I guess the only other thing maybe to say is the formulas get ugly. Maybe I should just say uglier, right? I don't know if they're that ugly. I mean, I might say they're beautiful. By the way, just to review, Chapter 8, we did a test statistic. I'm just curious because you guys have been doing a lot of homework lately. And you had one, well, I guess the one you used last night mostly was T because you were doing means. But then in section 8.3, I know you guys did one for z. Do you guys remember, like, do you just happen to have it memorized yet, what z is? Yeah? P hat, right? Minus P, yes. Yeah, and the funny thing is, no one ever told you to memorize it. It's just you've seen it so much and done it so much, you start to remember. You know what I mean? I'm telling you that in chapter 9, really our formula is this. But it's kind of expanded. You'll see. You'll see what happens. Watch. Let's flip through a few slides. Yeah. I hate when they make the print that small. You guys probably can't even read that, am I right?
You're right.
This section is based on proportions, but we can use the same methods for dealing with probabilities. Yeah, or percentages. Yeah, the little p stands for proportions, probabilities, percentages. Fine. Basically, they're trying to make the point that you're both going to do hypothesis testing and you're going to do confidence intervals also at the second half of this class. Hey, by the way, you see that P1? I think I already gave you that, right? And I don't know, can you guys see the little hat on top of this P1?
Mm-hmm.
They're giving you a formula. Have you seen that formula before? P hat equals what? X over N. We've seen that before. It's just that now they're putting numbers here. Here, I am going to write one of these down. Because I noticed on my formula page, I wrote down P1 and P2, and those are, right, this is the parameters. That's what we're trying to go after. But the statistics that we have are P1 hat or P2 hat. And for example, what does P2 hat equal? What would you say? How do you compute P2 hat?
X2 over N2?
That's right. That's right. Now, just so people are clear about what do I mean by 1 and 2, okay? Let's say that 1, population 1 are the women that we surveyed, and population 2 are the men that we surveyed. Sound good? Hey, let me do a quick survey. What proportion of women in our room drank coffee this morning? Not one?
You all lying.
Not one woman drank coffee before coming here. What proportion of men drank coffee? Who drank coffee here? Oh, you did.
Oh, okay.
1 and 1? I'll tell you what, you must be a morning person. I didn't even. You must be a morning person, right? And so I guess for the women, it looks like I just surveyed 6. So 1 out of 6 drank coffee. For the men, looks like 1 out of 4 drank coffee, right? I won't point out that the 2 coffee drinkers got here later than anyone else. Probably because they were getting their coffee. Don't worry, I'm not recording. Oh, yeah, I am. All right, now. So what happens now, these all would correspond, say, to the women, all these variables, right? We're going to put a little 1 or a little 2. So N1 in my example is 6, because there were 6 women I just surveyed. Right? X1 was 1. 1 out of 6 drank coffee. You guys follow? Hey, how about this down here? Q hat. Q hat. Does that make sense? What would that be for our example? Yeah, so what would it be? 1 minus P hat. Well, I guess if P hat is 1 out of 6, then Q hat would be 5 out of 6. That's right. I could do the percentages if you wanted. Russell, did you drink coffee this morning? Did you drink coffee this morning? Okay, 2 out of 5. The men are drinking more coffee? All right, anyways. Moving on. Here's something new finally. Finally something new. P bar, the pooled sample proportion. Okay, so P bar equals x1 plus x2 over n1 plus n2. So I guess in my example, maybe I can compute one over here. We had one woman drink coffee, we had 2 men drink coffee, and then let's see, there are 6 women in the room and there are 5 men in the room, right? So you could compute. See, the pooled sample proportion is really just if you kind of put the 2 groups together. That's why they say pooled. You put the groups together, you get 3 out of 11. Does that make sense? I don't think you even need a fancy formula as long as you know what it's doing. We're putting them all together when we pool them. So in my example, I guess, 3 of the 11 people in this room drank coffee this morning. 3 out of 11, right? That's my P-bar. Oh, and then something else they're going to say Q-bar. Well, what's Q-bar? Okay, so in our example, what would it be? Well, I guess it'd be 1 minus 3/11ths, right? So it'd be, how many 11ths would you have if you had, yeah, it'd be 8 11ths, right? 8 of us did not drink coffee this morning. So I guess this pooled sample proportion is different. Okay. So then, the requirements are that you have to have proportions from 2. There's a word we had in the past. Independent. Do you remember what that means? Yeah. The probability of Sierra drinking coffee, right? Whether or not Sierra drinks coffee doesn't affect whether or not I drink coffee. Would you guys say that's true? Okay. Let me show you a situation where it might not be true. Suppose I have a room full of husbands and wives. I would argue that the probability of drinking coffee there is not independent anymore. If you have, say, a husband and wife, the husband drinks coffee, I would argue it may be more likely the wife drinks coffee. I know for my grandparents, alcohol, right? One drank alcohol, the other did. And that was a factor in my well, he left, but my grandmother became alcoholic over the years. But she was a small woman and with a larger man that liked to have a drink here or there, but I think it affected her more and influenced her. So what I'm saying is, when you start having couples like that, we're gonna deal with that situation later in the chapter. We're talking about independent random samples. And guys, again, you guys know that my example of the classroom is definitely not a simple random sample either, right? We should take data from large population and randomly choose sets. And they say, by the way, you want to make sure it says the number of successes is at least 5 and the number of failures is at least 5. Hey, you know what that says to me? That says our coffee example is not going to give me a good value of P. Because look, I only have 3 out of 11 drinking coffee. If you don't have at least 5, both here and here, you're going to have trouble. Okay? So, yeah, bad example, Paul. Let's do one from the book. Well, we'll do that. Now, here's the test statistic. I'm going to write it down, but I want you to see, isn't it really the same thing we just had? Right? Check this out. Here's the old test statistic written in green. Right below it, I'm going to write the chapter 9 test statistic. It's still a z-value. Z equals. It's a big, ugly fraction. Well, even bigger this time. In the numerator, the first thing we're going to have here is a set of parentheses. It's just that instead of p hat, I'm going to have p1 hat minus, what do you think? p2 hat. Minus. And you guys know what's going to go here. Instead of P, we're going to write P1 minus P2. Okay? By the way, two of these four letters, variables, we're going to know, and two of them we really don't know. Which ones do we know when we do a study, and which ones do we really not know, but we're trying to estimate?
We know hat.
We know the hat ones, yeah. We don't know P1, and we don't know P2. Are you with me on this? Okay. Now, what does a typical hypothesis test look like? Let me show you. Remember that before you compute the test statistic, usually you're doing things like computing H0 and H1. And you guys have done this a lot by this point. What's the difference? How do you know what goes where and things like that? What can you tell me? The null hypothesis has equality, right? The alternative hypothesis, I'm just going to put a big question mark because it could have lots of things, right? Sometimes it has greater than, that's one tail. Sometimes it has not equal to, and that's two tail. Are you guys with me? But the fact that this has equality, well, what do you think it is that we're going to claim is equal in the null hypothesis? It's going to be P1 is equal to P2. Isn't that interesting? Do you guys think that the proportion of women that drink coffee is the same as the proportion of men that drink coffee? Do you think it's different? What do you think?
Yeah.
Who do you think drinks more?
Like population-wise?
We're talking population. This is what I'm asking.
Men.
You think men drink more coffee?
I think so.
See, no, I see now why you think that. Why it says that they're equal. It's not gender-based.
So if it's not gender-based, then right, the null hypothesis is that they're equal, right? Are you guys with me on this?
Yeah.
These are the kinds of questions we're going to ask about lots of different populations. It doesn't have to be coffee. You'll see, of course, many examples. And actually, this is really, really versatile. By the way, just a little algebra point. If you have this equation, P1 equals P2, it's actually quite helpful to subtract P2 from both sides, because what ends up happening is you're setting the equation equal to 0. So what is it that would equal 0? If I subtract P2 from both sides of that equation, I get P1 minus P2. Does that make sense to you? I subtract P2 from each side, and I get the blue equation. Are you with me on that? If you understand that, then you understand something about the formula. If we assume the null hypothesis, you know what's going to go right in that parentheses usually? A 0, which makes your formula not so complicated anymore. So that's kind of a nice little thing to understand also. Russell, question? You don't get what? That P1 minus P2 equals 0? Okay, let me try and explain it one more time. Here, we'll go over here to the margin. Again, let me zoom in for this too so I really explain it well. What is the null hypothesis? That's H0. I said it's P1 equals P2, right? Now I want to do a little algebra. I'm going to subtract P2 from both sides. You guys have done that before, right? I mean, that's how you do algebra. What do you get on the right-hand side?
0.
We get a 0. Right? On the left side, those are not like terms, so I'll just write P1 minus P2. Does that make sense? And now looking at the formula again, this is what I'm going to zoom back out because we don't need to be that big. But when you look at it, if P1 minus P2 is 0, what I'm saying is this big parentheses is usually going to be a 0 because we're assuming the null hypothesis when we do hypothesis testing. Okay? Now the denominator, I have to admit, it used to be just square root of PQ over N. Now it's not so simple. Let's write it down. Here it is. Whoa! It's a huge square root. Of what? P bar Q bar over N1 plus P. What does P bar stand for again?
The, like, total pool.
The pooled proportion. Yeah, we did that earlier, right? So again, I guess I should look at my paper, right? This P bar comes from here, and Q bar is just 1 minus P bar, just like it always was. And N1's the sample size for the first sample, and N2 is the sample size for the second sample. But other than that, guys, everything is almost exactly the same as chapter 8. So what I thought I should do today is go through a hypothesis test using this formula, and then I think we could push the other stuff off until after your quiz.
This is going to take the rest of the class. So what's wrong with it?
No, we have 45 minutes. It won't take that long. But I understand your concern. You guys learning some things, though?
Yeah.
Yeah, that's good. Like I said, I think this actually helps you cement what you learned in Chapter 8. And even Chapter 7, although I don't want to do that today because of your quiz. But Chapter 7, confidence intervals, we're going to understand those better after Chapter 9. So let's go to the example that I have. Oh yeah, like I said, confidence intervals. Remember the E? What's E stand for? Margin of error. Yeah, we'll come back to that. All right, here's my example. Yeah, I think I can. Let me see what the easy way to do that would be. Probably from here. There. Right? But then I got to push up here so you can see for a moment. The table below lists results from a simple random sample, front seat occupants involved in car crashes. Not a very pleasant topic for the morning, but important, right? Because they're talking about airbags, and then some cars don't have airbags yet, right? Well, older cars. They're required now, I think, in the new cars, right? So use a 5% significance level to test the claim that the fatality rate of occupants is lower for cars equipped with airbags. I mean, we hope, right? We hope, before we establish a law and require car companies to spend lots and lots of money to put airbags in all these cars, we hope we've done studies like this that show they make a difference. And thankfully, right? Most car crashes are not fatal, right? People in the front seat. Actually, it doesn't show how many had seatbelts on or not either, right? That'd be an interesting piece of data also. But we're going to take the data and we're going to see if we can run with it here. So how do you begin? You freak out because it's a word problem. But once you've gotten past that, wait, I'm not going to sit here and freak out. I seem to remember that every time that Paul did a chapter 8 problem, the first thing he did was try to write down the original, because that's what we're testing. So let's do that. Let's write down what's the original claim for this problem. And right after I write down the original claim, what I'm going to try to do is I'm going to try to write H0 and H1, right? So what's the thing being claimed here? Test the claim that the fatality rate of occupants is lower for those cars equipped with airbags. All right. And guys, the way the chart is, let's make population 1 be airbags and population 2 no airbags. You guys with me on that? Okay. So here I go. Let's see. Yeah, I started to write down original claim, but I realized I better say what's what. So, airbags, that's going to be population 1. And then no airbags, that's going to be population 2. And so the original claim, again, going back to it, would be, what about P1 and P2?
Would be P1 is less than
that's what it says, right? It says the fatality rate is lower.
So these are fatality rates. Wow, okay. P1 is less than P2. By the way, I want to come here and say, or, remember that you might write it this way. P1 minus P2, I'm doing the same trick I did before, is less than what? 0? That was that trick, Russell, I showed you, right? Same thing, it's just it has an inequality now. So, that's the original claim. And I know that after I have the original claim, what I like to do is I like to write H0 and H1. Okay? Where? Tell me what to do, guys. You guys should be able to do this by now.
It goes under the alternate.
I agree. This does not have an equality anywhere in it, so I'm going to throw the original claim down into H1. We're going to say P1 less than P2. Yeah, or again, you could say P1 minus P2 is less than 0. I think sometimes that's helpful to write. Okay, what would be the null hypothesis for this problem?
P1 is equal to
P1 is equal to P2. Or again, we could state it P1 minus P2 is equal to 0, right? Who's with me so far? Amy, good. Brandy, good. Kelsey, with me? Okay. So now, Jamie says, yay. All right, so here I go. I need to compute the test statistic. Whoa. A lot of stuff there. Well, I'll start to fill it in. Here I go. Z equals. Well, I have a lot of things to compute. I mean, P1 hat. Better come over on the side and do that. Did they give me P1 hat? Let's see. No.
P1 hat is supposed to be the fatality rate, right? How do you get the fatality rate for the first population?
Remember, there's a formula for P1 hat. Do you remember how you get it? X over n, yeah. So this is going to be x1 over n1. Again, 1 is the population with airbags. Do we have x and n for the population of the airbags? Yeah, 41 is definitely x1. That's the number that were killed, right? So that's 41. Now, that 11,541, I have to be careful. It does say total, right? So that is N1. Sometimes they'll tell you how many were killed and how many weren't, and you have to add them together. But here they gave me N1. So yeah, this is just 41 over 11,541, right? And then P2 hat, I'm going to have to compute the same way. I guess looking at the data, it's going to be 52 over 9853. Okay, so I have some computing to do here before I can even put it in the formula, right? All right, let's do that. P1 hat is equal to, well, let's see. We need 41 over 11,541 on my calculator. Oh, that's pretty small. Well, good. It's a fatality rate, right? Less than 1% of those that were in the car crashes were actually killed. 0.0035. What was P2 hat? Was it even smaller or bigger? Well, I'm claiming the airbags is safer, so maybe, let's see, P2 hat would be 52 out of 9853. Yeah, it's a little bigger, huh? 0.005, I'll say 3. So I'll round. Actually, if I'm going to round, I should really say 0.0036. Do you see that? Yeah, let's be consistent here, Paul. All right, so that's 0.003. 0.036 is P1. Okay, P1 hat. I guess now I can start filling things in. Let's see. So we have Z equals 0.0036 minus 0.0053 minus, you know what I'm going to put next? I say we're going to put 0 here. How come?
Oh, it's
That's the null hypothesis, right? It's coming from there. The null hypothesis is that P1 equals P2, and that would mean P1 minus P2 is actually 0. So that helps. Divided by square root of, holy moly, okay? I need P bar, and the formula for P bar is right here. I need to add x1 plus x2 over n1 plus n2. Let me do that real quick, guys. So P bar, let's see. Remember, every time you use a fraction, you really want to use parentheses. So it's 41 plus 52 divided by what?
You add 11.
Yeah, the formula says x1 plus x2 over n1 plus n2, right? Because we're pooling everything. Yes. Yes, 11541, that was the number that had airbags. And then there were also a bunch of car crashes that did not have airbags with people in the front seat. And so this would be the pooled fatality rate. Kind of makes sense. It would be something in the middle, right? So P bar, we could say, is 0.0043. All right. Let's see. I guess I'll write that down here. P bar is 0.0043. I also need Q bar. How do you get Q bar?
1 minus P bar.
Yeah, let me show you on the calculator. You can get that pretty easily. 1, and then the minus sign. And then what you can do, guys, to get this quickly, hit your blue second key, and then I think the minus sign, right? Doesn't that say ANS above it? And that gives you the answer. That if you not the minus sign, the negative sign. But if you type in 1 minus answer, it's going to give me 0.9957 if I round, right? Which is exactly what it should be. So Q bar is 0.9957. See, you're not kidding. This is taking a while. But I think it's worth doing. All right, so we throw these in the calculator now, right? Well, now we have to put them in the test statistic. So I need P bar Q bar over N1. So let's see, that will be, I have to write this carefully, 0.0043 is P bar times Q bar is 0.9957 over N1. What's N1? Oh yeah, you see it? 11,541. And then plus, I'll just say same over, because I'm running out of room, over the 9853. All right. So if I can calculate all that, we've got it. And I'm ambitious, so I'm going to do it all at once. You guys would like to get done with this anyways, so we can do some other things. All right, so calculate. Questions so far? No? Here we go. So I'm going to open parentheses. Tell you what I'm going to do. I'm going to hit enter. That's one way to get it. Or you could just type in 0.0043 minus, oh no, that's not right. Sorry.
Try again. Open parentheses, what do we have? 0.0036 minus point what?
0053.
There it is. 0053. Ah, shoot. Okay, and then once I have that, I close my parentheses. I don't need to subtract 0, right? That doesn't have to, you don't have to do that. Now I just have to do divided by, and then we have the square root, so let me hit second x squared over here. Where'd it go? Second x squared. There's my square root symbol.
For N1 and N2,
Yeah.
I can divide it after I multiply the P hat and the Q hat, or I'm so messed up with this. Go ahead, I'll watch it.
Ask your question again, Sierra.
I don't know if I could multiply the P hat and the Q hat and then divide the N1 and N2.
Oh, I see what you're saying.
How do I?
How do I put the thing in the calculator? That's what I'm trying to show you. Okay? So I have this first number. I'm dividing by. Now I'm going to do square root. And I guess the question is, do I need lots of parentheses here or not? Notice for me, the new calculator, when you type square root, it puts your cursor right under the thing. The older calculators, when you type square root, does it have an open parentheses? Does anyone have that on their calculator? Good. So either way, you should be good. I think you can just start typing in now the numbers. Watch. 0.0043 times 0.9957, right? Divided by 11,541. So that's the first fraction. Then a plus sign. Your calculator is smart enough to know it's going to compute the first fraction, then the second fraction, then it'll add them together. So I'll just put a plus sign now. And I'll type the second fraction, which looks very similar. 0.0043 times 0.9957, and then divided by 9853. Wow. We did it. All that to get that z is negative 1.89. Guys, is that an unusual z-score or not really? So we don't have a feel for that yet. Okay. Let's draw a picture of it. Here, this is important because the rest of this, other than the ugly formula I just did, everything else is on your test tomorrow, on Monday, your quiz. Here, you've got to be able to understand this. I wrote down my z-score, negative 1.89, right? We draw a picture. So where does that live? Lives on the bell curve, right? Because it's a z. What do we know about the bell curve? We know right in the middle is 0. Right? Where's negative 1.89? Well, here's negative 1, here's negative 2, so maybe right here, guys. I'm gonna do this. I'm gonna take that z-score and I'm gonna write it right here. Z equals negative 1.89. Okay? And so, I have a question for you. Is this a one-tailed test or a two-tailed test? You guys do understand that? Okay, because that's the H1. That's the same as the quiz. And so, what I'm going to ask for next is that we compute the p-value. So we take the test statistic and we're asking, hey, what's the probability? See, if that null hypothesis is true, what's the probability that I get something at least that extreme? What you're really measuring is, guys, is it unusual for me to be this far away, right? If P1 and P2 are actually equal, is it unusual for P1 to be this much less than P2? 0.0036 instead of 0.0053. Or could it just be that was chance? That's what we're trying to decide. So how unusual would it be to get something over here? That's the p-value. Remind us, how do we compute the p-value on the calculator? Yep, normal CDF. So let's go there. And we will do second distribution, normal CDF. From where to where? Is that lower bound okay?
Yes.
Yeah, we want a really small lower bound because we're going all the way to the left. What should the upper bound be, guys? Negative 1.89. Okay, let's type that in. So this is a good lower bound. For the upper bound, I need to use this negative sign. I got in trouble last time. Negative 1.89.
Can I make the lower, like, -1,000 or what?
You can. This says -1 with 99 zeros after it, which is small enough.
Yeah.
But -1,000 is fine, or -10 is fine even. Yeah. I'll paste that in. And I got a p-value of 0.0294. Did anyone else get that p-value? Good. Then you guys are doing this. I mean, this is on the quiz tomorrow, right? Let's get the p-value. So the p-value here is 0.0294. We will compare the p-value to what? To what from the problem?
The alpha.
Alpha, that's right. Alpha here is 5%. Yeah, the significance level, yeah. So the p-value is lower than alpha, right? Okay. So I guess I'll finish up. I guess I need more paper, so I'll do it on the next page here. Okay. So again, the p-value, this is the car crash problem. The p-value was 0.0294, and that is less than 0.05, the significance level, alpha.
Do we already know the significance level ahead of time?
What's that?
Do we already know that ahead of time, alpha?
Yeah, they said.
Oh, okay.
Let me show you again. See? Use a 0.05 significance level.
And so if it were a two-tail, then you would have to divide that by 2.
Now that's interesting. If this were a two-tailed test, I might get a different little answer then. Yeah, that's interesting. But yes, it's less than alpha. And so we would conclude what? What does this imply then? We reject the null hypothesis. But I can't just finish the problem that way. I have to say something in English. Right? Anytime I see we reject, I will say there is sufficient evidence, right? Because that's what you're looking for. You kind of, when you do statistics, you want to say, yeah, the study shows something. If you fail to reject, the study doesn't show anything. There's not sufficient evidence to do. But here I will say there is sufficient evidence. Now to what?
To reject the claim.
Well, let's see what it is we did. Did we reject? Yes. We rejected the null hypothesis, but what I really want to talk about is the original claim. The original claim was the alternative hypothesis, right? And that's cool, because if you reject the null hypothesis, then automatically you are supporting, right, the alternative hypothesis. Does that make sense? So I would say there is sufficient evidence to support the claim that what? Well, I know, what's going here next. The claim was that P1 is less than P2, right? But let's change that into English because we want to answer questions in English.
Fatalities of airbags
Yes,
are less than fatalities with no airbags.
that's right. The fatality rate, I will say, for cars with airbags is lower than the fatality rate for those without. So on your quiz on Monday, this is the kind of thing you would have to do. Obviously, I can't give a lot of these problems. Well, for one thing, your formulas are nicer. Secondly, you've practiced a lot. But I like going through it slowly the first time you see something new. And so that's what we did.